welcome to the deep dive. Today we're zooming right in on what you could argue is the internet's single most vital bit of math, the cryptographic hash function.
Yeah.
Specifically, secure hash algorithm 256. You know it as SHA 256.
It really is. Think of it like the ultimate digital fingerprint. And our mission today is to show you how this one, sort of unassuming algorithm, really powers trust across, well, so much of the modern world.
Like what?
Like Bitcoin, decentralized money, or Git for keeping track of software history reliably, even these super reproducible software systems like NIST.
Okay, let's break that down. SHA 256. Fundamentally, it takes any input data, could be a whole movie, could be just one word.
Right, anything.
And it spits out this fixed size 256-bit string. We usually see it as, what, 64 letters and numbers?
Exactly, 64 hexadecimal characters. And what makes that tiny string so incredibly powerful comes down to two core ideas, really.
Which are?
Okay, first, determinism. Feed it the same thing, you get the exact same 64 characters back every single time, no exceptions. That's bedrock for verification.
Got it. Same input, same fingerprint.
And second, the avalanche effect. This one's cool. Change literally one bit of the input, flip a 0 to a 1 somewhere.
Just one tiny change.
Yep. And the output hash, it changes completely. Utterly, drastically, unpredictably different. You can't hide tampering, not even the smallest tweak.
Okay, that makes sense. It's like a super sensitive fingerprint. If you smudge the original document even slightly, the fingerprint just explodes. Right. Let's see how this plays out. You mentioned three big areas. Let's start with Bitcoin. How does SHA 256 go from identity check to, well, creating digital scarcity?
Well, Bitcoin does something clever. It kind of weaponizes how hard it is to run SHA 256 backwards. We call that pre-image resistance.
Like, run it backwards. What does that mean? You can't just look at the hash and figure out the input.
Precisely. You can't. So Bitcoin forces these computers, the miners, into this massive computational guessing game. They just keep hashing block data over and over, tweaking a little number called a nonce, until purely by chance they find a hash that starts with a whole bunch of zeros, meeting the network's difficulty target.
So the work is just guessing, brute force.
Brute force hashing, yes. That computational cost is the proof of work. It's what makes adding new blocks expensive and secures the whole timeline, the blockchain. And here's a neat detail. Bitcoin actually uses double SHA 256.
Double. It hashes the data twice.
It does. Hashes it once, then immediately hashes the resulting hash again.
Why? Seems redundant.
It specifically guards against a known cryptographic weakness called a length extension attack. It just makes the whole thing, even more solid. Ironclad, really.
Okay, wow. So that's Bitcoin using difficulty.
Yeah.
How does Git use the same math to, as you said, guarantee history?
Git flips it around. It leans heavily on collision resistance. That's the property that makes it practically impossible, astronomically unlikely to find two different inputs that accidentally produce the exact same SHA 256 hash.
Right. The odds are vanishingly small.
Vanishingly small. So Git uses this to build what's called a content addressable file system.
Meaning the address is the contents hash.
You got it. Every file or blob, every directory structure or tree, and every snapshot or commit is identified purely by the SHA 256 hash of its contents.
Huh.
So if you try to sneakily change just one byte in some file way back in the project's history,
the hash of that file changes instantly.
right, and since commits hash their parent commits ID and trees hash their contents IDs, that one tiny change creates this inescapable cascade. All the hashes up the chain break all the way to the present. You literally cannot rewrite history without everyone noticing.
That's actually brilliant. Okay, third pillar, NIST. Building software with purity. How does SHA 256 enable that?
NIST tackles that age-old problem. Well, it works on my machine. It aims for bit-for-bit reproducible builds.
Something developers dream of.
Totally. It does this by treating a software build like a pure function in math. And to get the unique ID for a package, NIST hashes basically the entire build universe.
Not just the source code.
Oh no. Source code, yes, but also the exact compiler version used, all the build scripts, all the dependent libraries, even environment variables, everything that could possibly influence the outcome, all gets thrown into the hash calculation.
So if anything changes, even a tiny dependency update,
you get a totally different hash and therefore a completely different unique path in the NIST store, like NIST hash package name. This isolates everything. It's why NIST PayEggs, the big NIST package collection, achieves something like, over 90% reproducibility? The determinism guarantees it. Same input, same binary output, every time, anywhere.
Okay, those three are fascinating. Uses money, code history, software builds. Really innovative stuff. But stepping back, What's the biggest, maybe most foundational application of SHA-256 for just, well, everyone online?
Yeah, those are architecturally amazing, but if you think about sheer scale and just fundamental necessity, the most critical use is definitely within TLS SSL certificates.
Ah, HTTPS, the little padlock in the browser.
Exactly that padlock. That's usually SHA-256 or a related SHA algorithm working behind the scenes. Forget Bitcoin miners or Git commits for a second. This secures the basic trust layer of the entire web.
How does it do that?
It's essential for the public key infrastructure, the PKI. When your browser connects to your bank, SHA-256 helps verify the bank certificate is legitimate. It creates the digital signature on that certificate, proving the server is who it claims to be.
So online banking, e-commerce, all of it relies on this.
Pretty much all secure communication. We're talking trillions of dollars in transactions flowing daily, all fundamentally secured by the integrity guarantees that SHA hashing provides within that certificate system. A failure there would be catastrophic, far beyond just one cryptocurrency or code base.
Right, that puts it in perspective. Which brings us to a final thought then. Bitcoin, Git, NIST, they're brilliant, specialized constructions built on SHA-256's properties.
Absolutely. They show its versatility, but they're standing on the shoulders of the trust infrastructure that SHA-256 already built for the entire web. That foundational layer had to come first.
So maybe think about that next time you see that padlock or commit code or even hear about Bitcoin. It's often the same underlying mathematical engine, this SHA-256 function, this string of 64 characters quietly underpinning trust in so many different corners of our digital lives.
From digital cash to code history to just buying something online securely, it's quite amazing the reach of one cryptographic primitive.